Hello everyone. I'm Kevin from Team 21229 Quality Control. Today, I would like to share some of our experiences on how to optimize robot design. During the center stage season, the improved robot design greatly enhanced our robot's performance. Here's a 2+8 auto video that demonstrates our robot's performance. It's one of the few robots that can perform a 2+8 auto without extendos. Without improving our robot design, our robot wouldn't be able to achieve this performance. Therefore, I would like to share some of our experiences on how to optimize robot design. Due to time constraints today, I'll mainly introduce some design improvements in our intake and transfer system. First, when optimizing robot design, it's very important to pay attention to small details. Small issues or rarely occurring inconsistencies can affect the robot reliability, especially in auto. An example of this is how we improved our surgical tubing inserts for our intake. While it may seem like a small change, it helped prevent the intake from unexpectedly breaking and losing surgical tubing. As shown in the figure in the left, in our first version, we used a zip tie to secure the surgical tubing, which was placed around here. This required one part of the insert to be small enough for the zip tie to grasp the tubing tightly, which made the 3D printed piece weak and prone to breaking. Additionally, it was very difficult to install surgical tubing because of the very large round tip here. In our improved version, we made the end of the insert significantly smaller to make it much easier to install surgical tubing. We also gradually increased the diameter of the insert and then reduced it to be able to secure the surgical tubing without a zip tie. This design allows the surgical tubing to be easily secured without a zip tie while also being thicker and more structurally sound. Throughout the season, we did not encounter any issues with this new insert design, no breakage or any surgical tubing falling off. So this example can show how subtle changes in the design of a small part can significantly optimize its performance. Now I'll walk through an example of how we optimize the performance of our intake and transfer. During the season, we learned that an effective intake and transfer must maintain complete control over a game element at all times. Otherwise, game elements may move in unexpected directions, get stuck, or escape from the intake. To ensure this doesn't happen, the game element must remain in contact with each of the intake rollers or ramp at all times, which can be verified by testing the intake manually. At the beginning of the season, we encountered issues where the pixel would pop or fly out of the transfer ramp. To address this, we added 3D printed roofs and covers, which you can see the pieces in orange, along the transfer ramp to prevent pixels from moving in undesirable directions. For example, at the end of the ramp, we installed this roof, which was angled to smoothly guide the pixel to a more horizontal position when entering the deposit box. We also found that it was easy to control a pixel on a flat surface. However, when a pixel needed to change directions, as shown in this picture, it became a bit more difficult. If there wasn't enough space, the pixel may get stuck at turnaround points. But if there's too much space, the pixel can fly out or multiple pixels can get jammed inside. To solve this problem, we added a gecko wheel as a soft roof, as you can see here and here, near the turnaround point where the pixel changes angles within the transfer. This setup prevents the pixel from getting stuck and also guides it along the ramp. In this picture, you can see the pixel can slightly compress the wheel when changing angles and moving up. Sometimes Multiple pixels would get jammed near the top of the intake, and reversing the intake couldn't free them. That meant that the pixel would remain stuck for the rest of the match. We discovered that intake jams near the end of the ramp were extremely difficult to fix. Therefore, we added a small blocker in the middle of the ramp, which you can see here, to prevent multiple pixels from getting stuck at the top. This video demonstrates how our intake can handle possible jams. So when it detected it got jammed, it could easily reverse and spit out any extra pixels. We also wanted to be able to intake off the stack. For our first robot, we designed what we called 3D printed flappers, each controlled by a servo, to smack the bottom pixel out of the stack and into the intake. You can see this design in action here. And this design allowed us to achieve a 2+4 auto. However, this design wasn't the most consistent because it relied on the robots and pixels' orientations to succeed, and the flappers would occasionally get stuck on the pixel if it was aligned incorrectly. As you can see here, the pixel angle was slightly different from above, and therefore this caused the flappers to get stuck on each other in the pixel. As a result, the pixel wouldn't be able to enter the intake. So, in our next iteration, we designed what we call the deployable intake. It is wider and can intake pixels at any height on the stack.
Yeah.
So as you can see in that video, if it needed to get another pixel, the intake would lower to reach that pixel's height. This design also allowed our robot to be able to pick up from the stack very quickly, even if it was off by a couple of inches. This also allowed us to pick up 2 pixels stacked on top of each other during teleop. We also used sensors to improve the accuracy of our intake and transfer system. We installed 2 pairs of beam brake sensors in our deposit bucket, which you can see here and in these 4 orange circles. In each pair, one sensor emits an IR light to the other sensor, the receiver. If the receiver detects that the IR beam is broken, the robot knows that it has a pixel. This helps the robot reliably detect the number of pixels it has. For instance, during auto, the intake automatically reverses after the robot has collected 2 pixels, preventing possession of 3 pixels and avoiding penalties. If the beam brake sensors detect fewer than 2 pixels in the outtake, the deployable intake can lower to reach another pixel on the stack. We also connected the beam brake sensor signals to our LED lights. A blue LED light can indicate 1 pixel in our robot, and a green light denotes 2 pixels. This feature was very useful for us during teleop, as the driver could not see how many pixels they had in the robot. Instead, they could look at the color of the LED lights to determine if they're ready to score or if they needed to get another pixel. Now I'll present my last example where we added a backdoor mechanism to our deposit box. We designed a rotating door at the back of the box to release stuck or unwanted pixels from the robot, as you can see here, preventing pixel possession penalties. This also gave us the option to score pixels on the backstage if the outtake broke and we were unable to score on the backdrop. You can see this in action here. During auto, we always opened the feed door to eliminate any pixels that couldn't be grabbed by the outtake. As a result, the robot would always score something even if the outtake malfunctioned. Overall, this design provided the robot with more flexibility and mitigated the impact of unexpected failures. In general, these failsafes can optimize robot performance. Finally, these 3 videos show how the improvements I mentioned previously helped us a lot in auto. Having a wider intake meant that the robot has a larger error margin when gathering pixels, So even if its position was a bit off, it could still successfully intake. So you can see that the robot was kind of not directly at the pixel, but it could still pick it up. Having beam break sensors allowed the robot to automatically get rid of any extra pixels and prevent penalties. So you can see the LED light first turned blue, meaning that it had 1 pixel, and then it turned green. After that, the intake could automatically reverse to get rid of any extra pixels. And you can see it just spit a pixel out. Finally, the beam break sensors, if they detected fewer pixels, the intake will lower and the robot would move to get another pixel. So you can see the robot was waiting for a while and the LED lights were blue, meaning that it only had 1 pixel. After a while, it realized it couldn't get another pixel, so it moved to the side to get the final one. So that's the end of my presentation. I hope you learned something, and please let us know if you have any questions here or later through our Gmail. Have a great next season.
All right, thank you. Okay, so do we have any questions from our in-person folks? All right, we have one question.
What beam break sensors was he running?
Okay, so the question was, what beam break sensors are used in the deposit bucket?
I believe there were beam break sensors from Adafruit.
Thank you.
All right, any other questions? All right, if no more questions, thank you so much, Kevin. Let's give one last round of applause.